Okay, so for this project, we decided to do the M by N word square, and what that is, the problem is just for every row is a word and every column is a word, so you have words going both ways. And so to do this project, to do this problem, two approaches we use for backtracking and simulated annealing, and simulated annealing is what I will be explaining here. So for our dictionary, we used the NLTK dictionary, and I'm going to be honest, the words in here a little bit sketchy. I don't know if they're all real words, but that's what we used. And so this whole algorithm is based on whether those words exist in this dictionary. So if you had a different dictionary, it would also work. So here, the unwanted letters. I just took the least occurring letters in words in English, and I just took them out because I didn't want some of the words that those some of those letters to show up in the word square and then make it a little bit more difficult to find a solution. I didn't try it without those letters. Maybe I should have, but here we are. And then this is just them taking this function taking out the unwanted letters from the original dictionary. Here's a helper function to get the n length of words. So I use it down here in the to get the initial solution. So for first, I create a list of valid words with that helper function, and then from those valid words, I randomly choose them. Uh, so say I chose n rows was four and m columns was three. I would have four three-letter words. Here's my fitness function. I use prefixes and suffixes to determine whether or not, say, the word search is going in the correct direction. So I give, you'll see down here, I give them points for if any of the words contain those. Here you're just building the columns. And then this is just for debugging purposes, printing the solution, printing the columns. And then this is where we use that those above to actually calculate the fitness score. So in this case, the higher the fitness score, the better. And um, so if it's a complete word, say a five-letter word, all correct, we give it 5 points. If it starts with a common prefix or common suffix, give it 1 point. And right here, we're debugging it. Now, for another thing I also use to make sure we're sort of heading in the right direction is one-letter neighbors. So in this function, it basically makes, okay, for an example, say we had cat, and we wanted to replace the middle letter A. So the pattern for that would be C star T, and a whole bunch of words would be under there. So there would be caught, cut, cat would also be in there. We wouldn't want to include it, obviously. A bunch of other words. And so we would take from that pattern, take one of the existing words and replace that cat with, say, cut. So now A is replaced with U. And this is another helper column or helper function, is seeing which columns are actually real words. And if they are a real word, we don't really want to touch them that much. So we're going to make them locked. And then we're going to use that helper function down here, um, not allowing changes in locked columns. Anyways, the random neighbor, that's just the mutation function where we're looking for a better word square. Here, I made it a low 3 in 20 chance that entire row would be replaced with a new word. Otherwise, we're just doing that letter neighbor thing. And here, obviously, yeah, 90% chance we don't allow changes in locked columns. And if there's no available patterns or words with available patterns, we're just gonna replace the whole thing with a word. And then and then we get our new solution with our new word. in the specified row that we're changing. The main simulated annealing algorithm. I got this template from Geeks for Geeks, but I just replaced the parameters with my own. I changed all this. I changed. Um, this is generally the same, except for well, this isn't the same. This is all generally the same. This is what I put in. And here it were if the fitness difference is more than three, then we're just not going to take it at all. It doesn't matter if we're early in the algorithm. And then here this is just I had to change the whether it was like the originally it was if it was less than it was better, but now we want it to be greater than because higher fitness is better. And this is just saying whether or not we're going to accept it. And this is just more debugging. And then this is just, and then it returns the best solution and then that solution's fitness, and then the real words that are contained. And we're just going to run this really quickly so I can show you how it works. It's going to ask you for rows, columns, and then you'll see all the debugging stuff pop up right away. Come on, come on. Yeah, there we go. And here you see on the left here, that's the fitness of the solution that it's currently taking. And we're just going to let it come out here and see what we get. It was kind of tough. It's not a perfect system. See, we only got two columns correct. I found that it was really tough with simulated annealing to get it a correct word square, but with backtracking, it's obviously more exact. Um, this is the best I got. I'll let Hanan take it away with backtracking then.
Yay. So backtracking is a recursive approach, and we build a solution step by step and undo the choices when they fail. In the backtracking function, I follow this pattern and I try to fill the square row by row, testing each candidate word. So
Are you
if
gonna
we're,
share your Are you gonna share your screen?
oh shoot, you don't have mine up?
No,
Oh crap. Okay.
or I can go back. I think it's just right above mine here. I thought we were gonna switch up, but here we go.
My bad.
That is just more of okay. This is yours, I'm pretty sure. Yes.
Okay.
Yes, this is yours. Yep, go ahead.
Okay. Um, Let me just start over. So, backtracking is a recursive approach where we build a solution step by step and then we undo or backtrack from the choice when they fail. And then in this implementation, we try to fill the square row by row, testing each candidate word. And if the word causes an invalid column, the function backtracks and it removes the word with solution.pop and tries the next option. So we start out with prefix pruning, and this was highlighted in a Python read article that I'll attach in here. And the isValid prefix function checks whether the current letters in each column form the valid prefixes before fully committing to the word. This is pretty basic backtracking optimization or preventing the algorithm from exploring paths that can possibly valid lead to a oh my God, I'm losing my train of thought. Um, so it basically prevents the algorithm from exploring paths that can't lead to a valid square. And then we go on to the recursive portion. The base case is checking all columns, and if all the columns form a valid word, we return the solution. Otherwise, we backtrack. And then in our recursive case, we try every valid word in the current row. We skip words already in the solution, and then we skip words that would make any column like invalid. And then if a word works, we recurse to fill the next row. And if the recursion fails, we remove the word and try the next. Oh, running out of time. What does that mean?
We have time.
Okay.
Keep going.
All right. Um, but yeah, so when we check all columns are valid, we then accept the solution. And this is kind of from the article where the solution is valid only if it satisfies like all of the constraints. And then this is it. This is our backtracking portion of implementing the word square. Is that good? Do
Yeah,
we?
we're at like 11 minutes.
Okay.
You want to stop recording?
Yeah.
Perfect.